Hi there, and welcome to our third video in this Unit 1 video series. We're going to start this video out with a warm-up, and as always, try to use some mental math as you go. So take a minute to try these 6 problems. Alright, so let's go over these 6, starting here with number 1, simplifying radicals. We looked at this a little bit last time. 5 times the square root of 12. We want to think about how we can break up that 12 using multiplication. So we're going to have 5 times the square root of, we want to think about what multiplies to give us 12, in which one of those is a perfect square. So remember, your perfect square is 1, 4, 9, and that's really the only options right now. So it's going to be 4 times 3. 4 times 3 is 12. But because we have that 4 in there, now we can actually evaluate that part of the square root. So the square root of 4 is 2. So we have 5 times, this has always been multiplication out here in front. Square root of 4 is 2, and then on the square root of 3. So 5 times 2 is 10, so we have 10 on the square root of 3 is our final equivalent form there. Number 2, factor this quadratic. So we're going to think about 2 numbers that multiply to give us negative 33 and add to give us negative 8. As we kind of talked about last time, that's and why that works. Let's see, we have y equals, we have x times x is going to give us that x squared back. And then x times this number here and x times that number there, those are going to end up being like terms, so they're going to add together. So we need those 2 things to add to get negative 8. But then they're going to end up multiplying, those 2 things are going to multiply together to give us negative 33. So that's going to be negative 11 and positive 3. And the order in which you put those doesn't really matter. You can put the plus 3 first and then the negative 11. So as we talked about last video, this factored form is really going to help us to come up with a rough sketch of our graph. And we're going to look further into that today with even more factors than just maybe 2. All right, number 3, 2 to the negative 1. Again, in our last video, we talked about 2 to the 0, so let's continue that pattern on to negative numbers. So we looked at 2 cubed is 8, 2 squared is 4, 2 to the first is 2, 2 to the 0 is 1. And if we look at what's happening here, we're dividing by 2 each time we go down. So if we go down another integer value in the exponent, so it'll be 2 to the negative 1, again, we're going to divide by 2, and we're going to get 1 half. And you might say, well, that's just the reciprocal of 2, meaning this is 2 over 1, and if you flip that or reciprocate it, you get 1 over 2. So, and that's exactly right. Anything to the negative power is just going to be the reciprocal, and so 2 over 1 becomes 1 over 2. And you can think about what would happen if we continue this process. Divide by 2 again, and you get 1/4. Divide by 2 again, you get 1/8, and so on and so forth. And so you can think about negative exponents in that way. And so it's just the reciprocal to the positive integer value. Okay, so from there, let's go on to number 4. Which function type is this? I believe maybe 2 or 3 videos ago we talked about function types and those in general. This is what we call an exponential function. But it's not just any exponential function. This is what we call an exponential decay, and then it's decaying, it's getting smaller and smaller and smaller over time. And so that's what we call an exponential decay. Number 5, 102% of 40. So we talked about percents before, and we want to take the numbers involved and reducing or get rid of any trailing zeros. So really we're going to take 102 and multiply it by 4. 102 times 4, let's see, we can multiply by 2 twice instead of 4 at once. So 102 times 2 is 204, times 2 again is 408. So it's going to be some version of 408. So it could be 408, it could be 40.8, it could be 4.08, it could be 0.408. You really have to just make sense of the numbers involved now. 102%, that's just above 100%. 100% of a value is the value itself. So 100% of 40 would just be 40. Just over 100% should just be a little bit more than 40. And so it makes sense here that it is not 408, but 40.8. All right, lastly here, 126 divided by 4. It's kind of similar strategy there. We can divide by 2 twice instead of by 4 at once. So 126 divided by 2 is 63. So that's equivalent to 63 divided by 2. So we need to divide by 2 one more time. So that's going to be 30. So divide 60 by 2, you're going to get 30. And then 3 divided by 2 is 1.5. So we're going to have 31.5. All right, so our goal for today's lesson is to take what we learned last lesson about quadratics and apply them to larger degree polynomials. And we'll talk about what degree means here in a minute. But our goal is to graph polynomials from factored form and create a polynomial from its graph. Some key vocabulary words that we're going to talk about today are degree, which I just mentioned a minute ago, the fundamental theorem of algebra, and end behavior. So those are some key things that we're going to talk about today. All right, so last video we talked about quadratics, and quadratics had 2 factors, and we said that in this video we're going to extend that to more than 2 factors. So in this case we've got a cubic, and you can see the standard form of it up at the top here, and then the factored form below. And today we're not going to focus on how to get from standard to factored, but I wanted you to see both forms. And so really what we're going to focus on is how to take factored form and plot the graph, and so to find some key characteristics of the graphs. So the first one here, the first factor is x plus 2. So as we thought about last time, what makes that 0? So what value of x would make that parentheses 0? And of course that would be negative 2. Here, positive 3, so 3 minus 3 is 0. Positive 3 would make that 0. And then here, an x value of negative 1. So negative 1 plus 1 is 0. So using the zero product property, we can think about what values of x make each of those factors 0. And then from there, we can plot our x-intercepts. So our x-intercepts are negative 2, so negative 2, 0, 3, and negative 1. One other thing that we can also tell by looking at factored form is the y-intercept. So the y-intercept is the output whenever the input is 0. So let's input 0 for x and then see what we get out. So we put 0 in there, we're going to get 0 plus 1 is 1. Put 0 in there, we're going to 0 minus 3 is negative 3. 0 in there is 0 plus 2 is 2. So we have positive 1 times negative 3 is negative 3 times positive 2 is negative 6. So our y-intercept is going to be 0, negative 6. And you can see that point there. So from there we have our basic setup here of our points, our x-intercepts and y-intercepts, and then we can kind of put it all together to form these graphs. So if you can see here, this point is going to connect with these two directly. So it's going to come down through here, and then we don't know exactly how it acts, but it's going to come back up at some point and go back up through this point there. So we know it's going to end up going up and to the right, and we're going to talk about more about end behavior and what it ends up doing past our x-intercepts later, but we can see that general idea coming through here. And then it's going to come up, and then it's going to come back down through this x-intercept of negative 2, and then go back down forever and ever this way. So it's a very rough sketch of this graph, but some main things that we can definitely tell are the x-intercepts and the y-intercept. So when we think about end behavior, as we were mentioning a minute ago, what happens as we go way to the right, and what happens as we go way to the left? Is it going way up, 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 up to the left, or does it go down forever and ever to the left and to the right? So, so when we think about here, so these are all the degrees. So when we think about degree is the highest exponent in our polynomial. So in this case, when we go back here, this is a cubic for two reasons. One, the highest degree up here is 3. So that makes it a cubic. The other reason we know it's a cubic is because there are 3 factors of x. Because there are 3 factors of x, if we were to multiply those together, again, we would get a cubic out. So degree is the highest exponent in your polynomial. So if the highest exponent is 0, meaning it's just a constant, like a number, so like for example, y equals 4, it's just going to look like that. So you're not really going up or down, either way. If your degree is 1, it's going to be a linear function, so x to the first power, and that's going to go up to the right and down to the left, unless it's a negative x. So this might be a version of y equals positive x, and then this might be a version of y equals negative x. And so it kind of flip-flops. Instead of going down to the left and up to the right, the red one goes up to the left and down to the right. All right? And then if we're going to degree 2, so that's a quadratic, so maybe like some version of y equals x squared. It looks like this, so it's up to the left and up to the right. But some version of this could be negative x squared, where it goes like this instead, down to the left and down to the right. And so either one of those could be an option there. Here we have a cubic, which is degree 3, which could look something like this, or it could look something like that as well. So it's either down to the left and up to the right, or up to the left and down to the right. So those are the only 2 options with cubics. Degree 4, which is what we call a quartic function, is degree 4, and it looks something like this. Or it could look something, it loads here, but it could look something like that. So it's either up and up or down and down, similar to the quadratic. And then lastly, degree 5, which we call a quintic function. And it could be down to the left and up to the right, or it could be up to the left and down to the right. So I hope you start to see some patterns here between even degree polynomials and odd degree polynomials. And we're going to kind of throw out this 0 one here because it doesn't really act similar to the rest of these. It's really not a polynomial in this case. So let's start with degree 1, degree 2, 3, 4, and 5. And let me just pause for a second. Do you notice any patterns between the even ones and the odd ones? Okay, so hopefully you notice that the odd ones go in opposite directions. So opposite directions. So either up to the left, down to the right, or down to the left, up to the right. Whereas the even ones go in the same direction. So either down and down or up and up. So hopefully you were able to recognize that. So overall, we really have 4 cases. But let's get into why this occurs. So why does the highest power in our polynomial affect this? So for example, why does x cubed determine this? Why doesn't the 7x or the minus 6 impact this? So let's kind of get into that for a second. So if we look at this, we have this cubic up here. So we have x cubed minus 2x squared plus 3x minus 4. But really all that determines the end behavior is this part right here. None of the other stuff matters in terms of what it ends up doing at the far stretches of the graph. So let me explain why. So if we look at each component separately, so if we look at how x cubed impacts things, how the quadratic, how the linear, and how the constant impacts things, we can see the different values of these individual components at these x values. So at an x value of 0, the first 3 terms really don't impact at all. It's only dependent on the last value, which is our y-intercept. But the further we get away from 0, the larger the values are going to be for this x cubed spot. And the larger these are going to be as well, but not nearly as much. So the further we get away from 0, the more that leading term takes over the function and determines where it's going to end up going. So because a negative value cubed is still a negative value and a positive value cubed is still a positive value, that's where you get that up to the right and down to the left behavior. But if this were a negative x cubed, well, that would switch the signs of these. So it'd be plus here and minus here, which that gives us the opposite effect. So it would be up to the left and down to the right. And so we would see that happening here. So anyways, that just kind of gives you some understanding as to why is the leading term the highest power that determines the end behavior of a polynomial. So there are 4 cases. All right, we kind of already talked about them a little bit. There's up and up, down and down, up and down up. So there's really those 4 cases. So let me show you how to quickly identify which case you're in. So we have the degree across the top here. If it's an odd degree, for example, 1, 3, 5. So if it's a linear, a cubic, quintic, so on, then if the leading coefficient is positive, so if the number out in front of x cubed or x to the 5th or whatever is positive, then it's going to be down to the left and up to the right. However, if it's a negative out in front, it's going to be the opposite, so up to the left and down to the right. For example, let me give you a couple examples here. This one might be negative x to the 5th plus 3x to the 3rd minus 6x plus 1. Something like that might be an example. Whereas if you have an even degree, so if you have a quadratic, a quartic, even a degree 6 polynomial, which is not really a name for that, but if we have a degree 6 polynomial, that would work as well, or 8, so on. If it's positive, that means that you're going to end up going up and up. And again, there may be some stuff happening in between that, but in the far ends of the graph, they all behave the same. Or it could be down and down if it's a negative out in front of that. So an example of that one might be y equals negative x squared plus 1 or something like that. So we can see there are 4 cases there, and we're going to look at some other examples and see more into that. But let's go back to the one we already did. We kind of pieced this one together just based on what had to happen from here. It had to go through this point, because if it didn't, if it went somewhere up here and then back down through that point, well, then we'd have another x-intercept, and we didn't have another one. And so we know that it was going to come down through here and then go up through there and then continue on forever upward. Again, if it didn't continue on up forever upward, it would have turned and come back down and we'd have another x-intercept, but we didn't. So we know it just kept going up and up and up. So let's connect that with what we just learned about degree. So we have a positive, this is a positive 1 that we assume is out there in an odd degree. So in a positive odd degree was that case here where it's up, down to the left and up to the right. And that confirms what we did here, right? It ended up going down to the left and it ended up going up to the right. Now again, there's going to be stuff that's happening in between those bounds or those ends of the graph, but really just kind of want to know what happens on the very ends, because there's 4 ways we can characterize those for polynomials. Okay, so now that we know what degree is and we know what end behavior is, let's get into another example. So here we have a quartic function at the top there, where it has a highest power of 4. And again, below that is factored form. We won't get into how to get from that form to the other just yet, but we've got this factored form. So let's use factored form to see if we can graph this polynomial. All right, so our x-intercepts are -4, -1, 3, and 5. So let's go ahead and plot those. I'll do that in red. So -4, because that's what makes that 0. -1, that's what makes this 0. 3, and 5. Okay, now our y-intercept is actually going to be off the screen here, and that's okay, but let's go ahead and identify it. So the y-intercept is going to be the output whenever all of these x's are 0. So if we put 0 in here, we're going to get negative 5. Put 0 in here, we're going to get negative 3. So multiply those together, you get 15 times, put 0 in here, you get 1, it's still 15. Put 0 in here, you get 4. So 15 times 4 is 60. So the y-intercept is going to be way up here at 60. And we're not going to graph that, but that's okay. We've at least identified that the y-intercept is 0, 60, that point way up there. Okay, so let's go ahead and plot this. So if we think about our in behavior, this is an even degree and a positive number out in front. So that means we're going to be in that case that's up and up. So we go ahead and say that when we finish going through these zeros, we're going to end up going up and up. We know that that's the case. Okay? So it's going to start going from up, and it's going to come down through this x-intercept. And then we don't know exactly how far it goes down. That's okay. We're just going to do a rough sketch here. We know it comes down through here, and we know it's going to eventually turn and kind of, because it's got to go through this next x-intercept. And then it's going to go way up there to 0, 60, and then it's going to come back down. It's going to come back down through this x-intercept of 3, 0, and then it's going to turn around and come back up through this one at 5, and then it's going to eventually go up, 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 up. So that follows our in behavior. It works out with our x-intercepts. If you get the in behavior wrong, the y-intercept will actually tell you or alert you that you did it wrong. Let me show you real quick how that works. So if I start down here and I go up, and I go back down through this one, because I think that the end behavior is down and down maybe, and I try to go, and I have to cross the y-axis down here, but I know that my y-intercept is, and I can circle it here, is 60, then I know that there's something wrong. Because I need to cross the x-axis or the y-axis down here in the negative number. So that's what I mean when I say that the y-intercept can help you identify or alert you that you've made a mistake with your in behavior. So those two should definitely connect together. All right. So what we've seen here, and I hope you've gathered this, is what we call the fundamental theorem of algebra. And that is that any polynomial of degree n has n roots or x-intercepts or zeros. Okay? Now some of those may be repeated, and we'll see an example of that here in a second. And some of those may be imaginary, as you saw some imaginary solutions back in integrated math 2. But all in all, a degree n has n roots. So for example, if you have something that starts with x to the 7th, and whatever goes on, that means it's got 7 x-intercepts or zeros or roots. Now, again, some of those may be imaginary, so they may not actually be x-intercepts. And some of them may be repeated, but there are 7. So let's look at another example. So we have a cubic here. So its degree is 3, which means we should have 3 roots. Now again, some of those may be repeated or imaginary, but we should have 3 roots. All right, this one, this factor here gives us a root or x-intercept of 3. And this one, negative 2. But if you notice, this factor is squared, meaning we're taking that factor and multiplying it by itself. So another way to write this function is negative x plus 2 times x plus 2 times x minus 3. That would be an equivalent way. So if we did it this way, we'd have negative 2 from there, negative 2 from there, and 3 from there. So what we can say here is that if there's an exponent, that tells us how many times this root is repeated. Okay, we call that multiplicity. Multiplicity. So it's got a multiplicity of, in this case, 2, meaning there's 2 roots of negative 2. Now we still have an x-intercept at negative 2, so that tells us that we have a point there, and we have a point at 3. but the graph is going to look a little bit different because of that multiplicity of 2. So let's think about our end behavior. We have a negative in front of a cubic. So that's the case of a negative odd degree. So that means we're going to start up to the left and down to the right. So it's going to be up to the left, it's going to come through here. And then it's actually not going to come through there. It's going to touch there. But because it's a squared value there, it's going to act like a squared degree here. So, or degree 2 here. So it's going to act like a quadratic. So whatever the degree is of that factor, whatever the exponent is of that factor, it's going to act like that type of function at that point. So a quadratic looks like this, right? It looks like a U. So what's going to happen is, at that point, it's going to bounce off the x-axis and go back up, which makes sense because our y-intercept is a positive 12, which you can see in standard form there, or you can multiply, negative 3 times 2 times 2 times a negative 1 should give us 12. So it goes up here, all the way up here to 9, 10, 11, 12, something right around there, and then it's going to come back down through that point here, and on forever and ever to the right. So all of it comes together to form this graph, but this is the first time we've seen a multiplicity. So there are still 3 roots, 3, negative 2, and negative 2. It just so happens that one of them is repeated, so we only have 2 x-intercepts. And so hopefully that kind of gives you an idea of what that looks like. So real quick, if we have a degree 1, so if we have a factor that looks something like this, so it's just to the first, so it's a degree 1. At that 0, or our x-intercept, it's just going to go straight through, like a linear function. If we have something squared, like I said a minute ago, it's going to bounce off of that, so it's degree 2, it's going to bounce off of that point and go back. So it's going to look like that, or maybe something like that. Okay, if we have a degree 3, so exponent of 3, that's degree 3, so it's going to look like a cubic at that point. So it's going to have a little changing in the concavity or curvature. So it's going to come through, but see how it changes concavity there? Or it could go like this. It starts below, it's going to curve up like that. And so the degrees after that look very similar. Evens after that look like this here. Odds after that look like this here. Whatever the degree is or exponent is, you can adjust based on that idea there. All right, so lastly, let's go backwards. Let's take a look at this one and see if we can go backwards. Given this graph, let's create factored form. So let me give you a minute to try this on your own. Okay, so if we look at our zeros here, we have negative 2, so that means it's going to be a factor of x plus 2. Here's an x-intercept of negative 1, so it's going to be x plus 1. And then we have an x-intercept of 10 here, so that's going to give us x minus 10 as we go across there. All right, now let's check a few things. One is the y-intercept. So if we put in 0 for x, do we get out negative 4? Let's check it. Put in 0 for x here, we get negative 10. Put in 0 for x here, we get 1. Negative 10 times 1 is negative 10. Put in 0 here, we get 2, so we get negative 20. So right now, by putting in 0 in for x, we get negative 20. So the x-intercept or y-intercept would be negative 20. But that's not the case, right? We actually have a y-intercept of negative 4. So we need to put a number out in front here so that when we get out negative 20, we multiply by this number out here and we get negative 4 out instead. And what's going to do that is a positive 1/5. Because we get negative 20 out, multiplied by 1/5 is basically dividing by 5, and you get the negative 4. So that's going to be a really good representation of this graph, this graph here. So that's kind of how to go backwards and kind of thinking through that. Okay, so hopefully at least an introduction to some of these concepts that we've been talking about. Graphing polynomials from factored form, mainly taking those factors and finding the corresponding zeros. But then also creating a polynomial from its graph, which we just got done doing. And then throughout this whole process, we've been talking about terms like degree, which is the highest exponent in a polynomial. We've been talking about the fundamental theorem of algebra, which is that highest exponent or degree should match the number of roots you have, although some of them may be repeated or imaginary. And then lastly, we talk about in behavior and the 4 cases that we could be in with in behavior, and how to recognize which case you're in and how that helps you graph the polynomial. So again, hopefully that's a good introduction to these ideas. In our next video, we're going to talk about more characteristics of polynomials and get into more detail with in behavior. And we'll hope to see you then.